Somewhere off the southern coast of China, there's a road that keeps going long after the land has already run out. It stretches past the last beach, past the final strip of visible coastline, and out into open ocean, water deep enough to hide a 10-story building underneath it, and wind strong enough to flip a loaded truck onto its side. Then, right when it looks like this road has finally run out of ocean to cross, it simply vanishes. It sinks straight down into a tunnel resting on the seafloor so that some of the largest cargo ships on the planet can sail directly overhead without ever knowing there is a highway running beneath their hulls. This is not really a bridge, and it is barely even a road in the normal sense. It is one of the most extreme engineering projects ever finished by human hands, built to survive a magnitude 8 earthquake, a top-level super typhoon, and a direct hit from a fully loaded cargo ship, all three at once if it ever had to. When early details of this project reached engineers in the West, the same people who had built the Golden Gate Bridge and the George Washington Bridge, many of them looked at the plans and said it simply could not be done. Not in that ocean, not over that seabed, not on that kind of timeline. China built it anyway, and by the end of this video, you will understand exactly why nothing quite like it exists anywhere else on Earth, and why the engineers who worked on it still describe parts of the build as something they were genuinely unsure would actually hold once the ocean tested it for real. To understand why this crossing is considered one of the hardest engineering problems anyone has ever solved, you first need to understand the water it crosses. The Pearl River Delta is one of the busiest, most economically important, and most physically demanding stretches of water on the planet. It links three major cities together, Hong Kong, Macau, and the mainland city of Zhuhai, and for decades the distance between them was measured in hours rather than kilometers. A truck carrying cargo from Zhuhai to Hong Kong had exactly two real options. It could drive close to 4 hours around the entire delta on congested mainland roads, or it could load its cargo onto a ferry and simply hope the weather cooperated. There was no direct route across the water, and that was not because nobody wanted one. It was because almost nobody believed one could actually be built. The total distance to cross is roughly 55 kilometers of open water, which is more than 19 times the length of Manhattan Island laid end to end. For comparison, the Golden Gate Bridge, the bridge most people picture the moment they hear the word bridge, is under 3 kilometers long from end to end. This new crossing needed to run almost 20 times that distance, not across a calm, sheltered bay, but across open sea that is genuinely hostile for most of the year. This part of the South China Sea sits directly inside the path of some of the most violent typhoons anywhere on the planet, with wind speeds during a direct strike capable of passing 250 kilometers per hour. Beneath the surface, the seabed in several sections is made of soft marine clay, exactly the kind of ground that can slowly swallow a poorly designed foundation over the years. And running straight through the middle of the crossing zone sits one of the busiest shipping lanes on the entire planet, with hundreds of massive cargo vessels, some carrying tens of thousands of containers at once passing through every single day. Any bridge built across this stretch of water would need to be tall enough to let those enormous ships pass safely underneath it. But that same shipping lane also happens to sit almost directly beneath the final approach path for Hong Kong International Airport, one of the busiest airports anywhere in Asia. A bridge tall enough to clear the largest cargo ships would be far too tall for aircraft coming in to land nearby. This is exactly the kind of problem that would cause most countries to simply declare the crossing impossible and leave it as a permanent ferry route. It is the sort of conflicting requirement that usually ends a project before it even reaches the design stage, because satisfying one requirement automatically breaks the other, and there is no obvious middle ground between a bridge tall enough for ships and one short enough for planes. China's engineers looked at that same tangle of problems and designed something that almost nobody outside the country believed could actually work, a structure that quietly turns from a bridge into a tunnel in the middle of the open ocean, with no visible seam where one method ends and the other begins. Here's the detail that made engineers in the West stop and look twice at the blueprints. For most of its length, the crossing behaves like an ordinary bridge, 6 lanes wide, resting on enormous concrete piers driven deep into the seabed below. But as it nears the busiest section of the shipping lane, the roadway does something almost no infrastructure project in history had attempted at this scale before. It sinks. The road descends onto 2 artificial islands built specifically for this purpose, and then, between those 2 islands, it disappears completely underwater, becoming a 6.7-kilometer tunnel resting directly on the seabed, deep enough that the largest container ships on Earth can pass straight overhead with plenty of room to spare. Stop and think about what that actually requires in practice. Engineers were not carving a tunnel through solid rock the way tunnels are usually built. They were assembling one piece by piece directly on the ocean floor, in a stretch of sea famous for violent storms and shifting currents. The tunnel was built from more than 30 individually cast concrete sections, known as immersed tube segments, each one roughly 180 meters long and weighing somewhere around 80,000 tons, heavier than the Eiffel Tower. Each one of these giant segments had to be cast on land, floated out to its exact coordinates on the open sea, lowered with extreme precision, and then sealed against its neighboring segments so tightly that not a single drop of seawater could ever find its way inside. If even one of those seals had failed under pressure, the result would not simply be an engineering setback. It would be a catastrophe unfolding directly beneath a 6-lane highway used by tens of thousands of vehicles. Engineers who reviewed early plans for this tunnel openly questioned whether this level of precision was even achievable at this scale, in open ocean conditions, on a construction schedule this demanding. Immersed tunnel construction existed before this project, but it had never been attempted at this length, this depth, or in waters this exposed to typhoon activity. Enormous waves regularly battered the artificial islands anchoring the tunnel, sitting directly inside a corridor that typhoons pass through almost every year. China's engineers did not just manage to finish the tunnel, they finished it with a level of accuracy that genuinely surprised international engineering observers, reporting a project so precise that essentially none of the segments needed any significant rework after being installed, an outcome that many experienced tunnel engineers considered close to unbelievable for a project operating at this scale. Before that tunnel could exist at all, the 2 artificial islands anchoring it had to exist first, and neither of them was there to begin with. Engineers needed solid, stable ground in the middle of open ocean, in water reaching more than 40 meters deep in some sections, sitting on a seabed made of soft marine mud that could not support a traditional foundation. Ordinary land reclamation, the slow process of dumping rock and sand until an island gradually rises out of the water, would normally have taken several years to complete. And on this project, the schedule simply did not allow for that kind of timeline. So the engineering team designed something that had never been used at this scale anywhere in the world before. Enormous hollow steel cylinders, some as tall as a 20-story building, were driven directly down into the seabed, almost like giant drinking straws pushed into wet sand. More than 100 of these steel cylinders were sunk into position to form a solid perimeter ring. Once locked into place, the space inside that ring was filled in, creating a stable artificial landmass strong enough to support roads, tunnel entrances, and buildings on top of it, all completed in roughly a single year, a fraction of the time that conventional reclamation methods would have required for the exact same job. This particular method, using giant steel cylinders sunk directly into the seabed, had never been attempted before, at this depth or at this scale anywhere on the planet. It was invented specifically because nothing that already existed could solve the problem fast enough or strong enough for what this crossing demanded. Every single part of this crossing was designed around one number, 120 years, which is how long the entire structure is engineered to remain in service. That is more than double the design life of most major bridges built anywhere else in the world, including in the United States, where the average major bridge is typically designed for somewhere between 50 and 75 years of service. To hit that number in this particular location, engineers had to design for the worst realistic version of nature that this stretch of coastline could throw at it. The bridge and tunnel system is rated to withstand an earthquake measuring roughly 8 on the standard magnitude scale, strong enough to sit among the most powerful earthquakes ever recorded anywhere on Earth. It is rated to withstand a top-category typhoon with sustained winds strong enough to shut down entire cities and ground every single flight in the region. And in a detail that genuinely surprised engineers when it was first published, the bridge's piers were designed to survive a direct collision from a fully loaded cargo vessel, weighing roughly 300,000 tons, close to the size of the largest oil tankers on the planet, without the overall structure collapsing. For comparison, most bridges built in the West are engineered around a maximum collision scenario far smaller than that, because a direct hit from a fully loaded supertanker is normally treated as such an extreme unlikely event that most bridge designs elsewhere simply do not plan for it at all. In the Pearl River Delta, with hundreds of massive ships passing through every single day, engineers had no choice but to treat that scenario as something they had to design for directly, not as a rare exception they could quietly ignore. The raw scale of materials used on this project is difficult to picture in your head, so here is what the finished crossing actually required. More than 400,000 tons of steel went into the bridge sections alone, enough steel by some engineering estimates to build roughly 60 separate replicas of the Eiffel Tower. Close to 1 million cubic meters of concrete were poured across the piers, the artificial islands, and the tunnel segments combined, enough to fill hundreds of Olympic-sized swimming pools from edge to edge. The total cost of the project has been estimated at somewhere around $20 billion, once every connecting section, port facility, and immigration checkpoint on both sides of the crossing is included, making it one of the most expensive single infrastructure projects ever completed anywhere in the world. Roughly 9 years passed between the true start of major construction and the day the crossing finally opened to traffic, with tens of thousands of engineers, welders, divers, and laborers involved across the full length of the project at its peak. Underwater, specialized diving teams carried out thousands of individual dives to inspect, align, and seal the tunnel segments by hand, Working at depths where visibility could drop to almost nothing and currents could shift without warning, a category of construction labor that ranks among the most physically demanding engineering work performed anywhere on the planet. It is worth pausing here because this is exactly where comparisons to Western engineering usually get misunderstood. The United States has produced genuinely incredible bridges of its own. The Golden Gate Bridge remains one of the most recognizable structures on Earth. The Chesapeake Bay Bridge Tunnel, completed in Virginia back in the 1960s, was actually the first crossing in the world to combine a bridge and an undersea tunnel system in a similar way, and for decades, it was considered one of the most ambitious engineering achievements in American history. But scale changes almost everything here. The Chesapeake crossing runs a little over 28 kilometers. This Chinese crossing runs 55 kilometers, nearly double that length, through far more hostile ocean conditions, using tunnel immersion techniques refined decades after the Chesapeake was originally built and designed specifically to survive typhoon and earthquake conditions. The Chesapeake crossing was never built to handle in the first place. The honest way to frame this comparison is not that China simply did the job better than the engineers who came before. It is that China took a technique the world already understood in a limited form and pushed it much further than anyone had previously attempted, combining a length, a depth, and a hazard level that nobody had ever tried to combine into a single structure before. That is the part that consistently catches Western engineers off guard when they study this project closely. It is not that the underlying idea was new, it is that nobody else had been willing, or perhaps able, to build it at this scale, in this amount of time, in water this genuinely dangerous. So what actually changed once the crossing opened? Before it existed, moving goods between Zhuhai and Hong Kong by road meant a trip of close to 4 hours around the delta. After it opened, that same trip dropped to well under 30 minutes. For a region responsible for an enormous share of global manufacturing and shipping output, cutting a 4-hour journey down to 30 minutes is not simply a convenience for commuters. It genuinely restructures how an entire economic region functions day to day. Factories based in Zhuhai suddenly gained much faster access to Hong Kong's port facilities and its international airport. Logistics companies redesigned entire supply chains around the new travel times almost immediately. 3 separate economic zones that had effectively been isolated from one another by water for generations began operating far more like a single connected region. Property developers, freight operators, and even tourism boards on both sides of the crossing quietly rewrote their long-term plans. Once 30 minutes became the new baseline travel time instead of a 4-hour round trip through congested mainland roads. This economic transformation rarely makes it into the headlines about the world's longest sea crossing, but it is arguably the real reason the project was ever worth building in the first place, far more than the impressive engineering statistics alone. No project of this size comes without real controversy, and it would be dishonest to pretend otherwise. The crossing faced genuine criticism during construction, including concerns over worker safety incidents, cost overruns beyond the original budget, and serious questions from environmental groups about the impact on the local population of Chinese white dolphins living in the delta. Engineering teams responded by adjusting construction methods and schedules in an attempt to reduce disruption to the dolphin population, including changes to piling schedules and the installation of ongoing monitoring systems, though environmental groups continued to debate how effective those measures actually turned out to be in practice. What even the harshest critics of the project's cost and process generally did not dispute was the underlying engineering achievement itself. When international structural engineering bodies reviewed the finished crossing, the tunnel and artificial island construction techniques were recognized as genuine advances in immersed tunnel engineering, methods that are now being studied by engineers in other countries who are planning their own extreme sea crossings. It is also worth remembering that even after opening, a crossing this complex does not simply run itself without ongoing effort. Traffic moving between Hong Kong, Macau, and mainland China has to switch between different driving rules and immigration systems along the way, since the 3 regions operate under separate legal and administrative systems, even while sharing the same physical road. Special checkpoints, dedicated shuttle bus services, and permit systems were all built specifically to handle vehicles crossing between these different jurisdictions, adding an entire layer of logistical planning on top of the physical engineering challenge. None of that complexity shows up in dramatic photographs of the bridge disappearing into the sea, but it is very much part of what makes a crossing like this genuinely difficult to operate smoothly on a daily basis, long after the concrete has already set. To really appreciate what this crossing achieved, it helps to place it next to other famous bridges people already know well. Japan's Akashi Kaikyo Bridge, connecting Kobe to Awaji Island, held the record for the longest suspension bridge span in the world for decades, and remains one of the most respected engineering achievements anywhere in Asia, stretching at just under 4 kilometers. This Chinese crossing runs 55 kilometers, roughly 14 times that length, though it uses a completely different combination of bridge, island, and tunnel engineering, rather than a single continuous suspension span. Denmark's Great Belt Fixed Link, connecting two of the country's main islands, was considered one of the most ambitious sea crossings anywhere in Europe when it opened in the late 1990s, combining a suspension bridge and an undersea tunnel across roughly 18 kilometers of water. For years, it was one of the closest things in the Western world to what this Chinese crossing eventually became, yet it covers barely a third of the total length and was never designed around the same earthquake or super typhoon requirements. Even the Øresund Bridge, the striking bridge and tunnel connecting Denmark and Sweden that many people recognize from film and television, spans just under 16 kilometers in total, a genuinely elegant piece of engineering, but still less than a third the length of the crossing this video is about. None of this is really about declaring an outright winner. Every one of these projects solved a real problem for the country that built it, under real constraints, using the best technology available at the time. But when engineers in America and Europe reacted to the completed scale of this Chinese project, the consistent reaction was not disbelief that China had managed to build a large bridge. It was disbelief that anyone had managed to combine suspension-level span distances, immersed tunnel technology, artificial island construction, and extreme disaster resistance requirements into a single 55-kilometer structure on a construction timeline measured in years rather than decades. The engineering numbers naturally dominate most conversations about this crossing. But underwater construction on this scale ultimately comes down to human beings performing extraordinarily dangerous work far away from any camera. The specialized diving teams responsible for guiding each tunnel segment into place worked in conditions most people would find almost impossible to imagine. Visibility, at the required depth, could drop to nearly nothing because of sediment stirred up by ocean currents. Divers worked with precision instruments to guide segments weighing tens of thousands of tons into exact alignment, with tolerances smaller than a few centimeters, fully aware that a serious miscalculation at that scale would not be a minor inconvenience. It would be a project-ending failure. Engineers on the surface later described the sealing of each tunnel joint as one of the most tense phases of the entire 9-year build, because every single seal had to hold under enormous water pressure indefinitely for the whole structure to ever be considered safe for public use. And there was genuinely no way to fully test a seal except to complete it and then monitor it under real operating conditions afterward. Divers often worked in rotating shifts around the clock whenever weather windows allowed it, because a calm stretch of sea in typhoon season could close again within hours, and any delay in sealing an already lowered segment risked leaving it exposed to shifting currents for longer than engineers were comfortable with. This is the part of mega project engineering that rarely gets mentioned in headlines about the world's longest or the world's biggest structures. Somewhere beneath the surface of the South China Sea, ordinary construction workers and engineers spent years quietly solving a problem that had never been solved at this depth or scale anywhere on the planet, and very few of them will ever be publicly recognized for it. Picture standing at the exact point on one of the artificial islands where the bridge disappears into the tunnel. Behind you, 6 lanes of traffic stretch back toward the mainland, elevated high enough above the water that a typhoon could be raging beneath the roadway while you remain safely above the worst of it. In front of you, the road simply vanishes into the ocean, with no ramp warning you and no sign announcing it. The highway just goes under and stays under for more than 6 kilometers, while some of the largest ships ever built pass silently overhead. There is nowhere else on the planet where you can stand in that exact spot and feel both of those realities at the same time. A bridge built to survive an earthquake capable of leveling entire cities, and a tunnel built to let you disappear beneath a typhoon while it tears apart everything happening on the surface above you. Most drivers crossing it barely notice the exact moment the road tips downward and the daylight disappears above them, which is in some ways the strangest part of the entire achievement. A structure this extreme was built specifically so that using it would feel completely ordinary. Somewhere off the coast of southern China, there is still a road that does not end where the land ends. It survived 9 years of construction, more than 100 giant steel cylinders sunk into the seabed, dozens of tunnel segments sealed by hand at the bottom of the ocean, and a design standard built to outlast almost every other bridge on Earth. And it is still out there right now, carrying traffic across 55 kilometers of open water, disappearing beneath the waves at exactly the point where the largest ships in the world need to pass. It stands as proof that even the hardest engineering problems on the planet are not truly impossible. They are simply waiting for someone willing enough to actually go and build the answer, one steel cylinder, one tunnel segment, and one sealed joint at a time.